Hello, a very good evening. Yeah, okay, just let me share my screen. Yeah, I got some questions in the chat box, but since I just logged out, so it's not visible anymore. Can you just ask those questions? Yes, yes. Okay, centrosymmetric or not, there's a simple thing is there must be some inversion symmetry or mirror symmetry. Like there are 11 law groups, we call them as centrosymmetric. Like one in triclinic, you can say one bar means there is inversion. Then in monoclinic, 2 by m means twofold is also there, perpendicular mirror also there. So that's how you can identify like which one are the centrosymmetric ones. Like then MMM, 4 by M, 4 by MMM, all those things. Like 3 bar, 3 bar M, 6 by M. Those are like 11 log groups are there, law space groups. So from there you can check. Ah, center. Yes, yes. Ah. Hmm. Is it a actual space group? Like, can you give some example? Like, P by first of all, P by M, it won't be possible because you should understand, like you are saying, like P by MBL, let's say this one. So P is for primitive cell, right? Primitive primitive cell means if this is a cell, there are four atoms, like due to translation, and this slash means let's say this M is perpendicular to something. So you have must have seen like P6 by MMM, let's say. So there's something must be here on which mirror will be like perpendicular, right? Here it is not defined, right? And in every space group, you can see that there must be a P or C or I or F, like things like C for centered, like there should be something here. Then F for this face centered, then I for body centered, like those things are there. Okay. And for MMM, yeah, this is a mirror, simply mirror. And okay, how can you understand? First of all, these things is not possible. Like theoretical, it's not possible only, right? And like you should see there must be something like some fold axis, like principal axis on which like the mirror or glide plane, whichever whatever will be there, right? Like that you can identify. Huh. Okay, thank you. So yeah, last day we are learning about what are basic motifs, what are the basic Yeah. What are the bases or motif? Then lattice points. So lattice is a mathematical concept, and the motif or basis are the real, points. Like if this is a, or let's say this is a motif or basis, and these are the lattice points. Now, in this motif, will sit on this lattice points and will repeat through translation. Like this, it will come here also, here also, here also, here also, and whole we can say as a unit cell or the crystal structure. Right. So we learned about what are the unit cells, how many types of crystal systems are there. Those are the seven, like cubic, tetragonal, orthorhombic, monoclinic, triclinic, trigonal, hexagonal. And there are certain conditions like minimum symmetry operations required for like to exist such as crystal systems. Like what will be their length conditions, like axial length conditions of the unit cell or the interaxial angles. Those are certain conditions are there. Those are three-dimensional unit crystal structures, whereas two-dimensional structure crystal in two-dimensional crystal systems, I have mentioned there are four types are there, like oblique, rectangular, hexagonal, and square. You can just go through that video, YouTube video, if you don't know. And like symmetry, we discussed about the symmetry elements and what are the symmetry elements and what are the symmetry operations, right? And no, what did we do last time? Yeah, this 2D and 3D one and symmetry elements. Then we talked about the glide, what the glide planes, what are the screw axes, right? So let's move on to the basic thing like about X-ray diffraction. So today we'll learn a little bit about the X-ray diffraction and all. Then we'll solve the practice questions because the assignment dates are still not covered. Like tomorrow is the final deadline, so I can't solve it before tomorrow. So in the next class, maybe we can solve both the first and second assignments. Before that, today we'll do just only the practice sets. So let's start today's class. So I have already told about X-ray also, like X-ray, what is X-ray as in a electromagnetic spectrum, and under which wavelength it stays, and why is it so important? Like why are we considering X-ray only? Because around the crystal structures that exist in our nature around has 2 to 3 Armstrong of lattice plane distances, and those distance are like quite relatable to the X-ray wavelength. X-ray wavelength fall in that region only, like around 10 nanometer. That is in Armstrong, you can say 1 Armstrong like that. And so we also have known the what are the difference between spectroscopy or diffraction. Like we call UV as a spectroscopy, NMR as a spectroscopy, IR spectroscopy, Raman spectra. But we call X-ray diffraction patterns. Like so, what are diffractions? So the diffraction pattern we get when uh, the radiation scattered by any object, right? So there are two types of diffraction pattern by X-ray we have seen. Like one, you will see in the diffraction pattern, if you like if you anywhere seen or you have collected the diffraction patterns by experiment, you must have seen these spots, and sometimes you will see spots but somehow like in circular shape. Yeah, spots but in circular shapes. So what happens is when you have a crystalline material, then you will see this straight spots in the reciprocal space. Whereas if it is a polycrystalline material, then you will see this kind of ring type of structure. So by seeing the diffraction pattern only, you can differentiate between this crystalline or polycrystalline material. In sometimes when we collect the single crystal XRD data, sometimes we get this polycrystalline only. And even if you take the raw data and try to solve it in OLX and other softwares, you will get you won't get a good reciprocal lattice. In the reciprocal lattice, you will get several of junk spots, which then you have to omit and you have to correct through the software and all. So that's a huge task. So always try to, if you are collecting a single crystal XRD data, always try to collect a clean data and within a like zero point 0.8 Armstrong circle like space. If you ever collected in the software, you can see on the Apex software mainly we use. So there you can see, and a good data must contain this much space must occupy and sharp spots in the reciprocal lattice, and like that will be good for your integration, and uh, then you'll be able to solve the crystal structure. So you all know that X-ray is discovered by the German physicist W.C. Röntgen. So basically, he was working with cathode tubes, and yeah, I just got the question. What is a polycrystalline material? So single crystal and polycrystalline. So from the definition itself, you can understand that there are but both are crystalline, right? Not like amorphous. There is, you have to understand the basic difference between a crystalline and amorphous material. Crystalline material has long range ordering or like repetitive arrangement. That's the definition of crystalline. Amorphous, that it doesn't have. Right. Now, among the crystalline material, there are two types of crystalline materials, single crystals and polycrystals. So poly means more than like one single crystals, like right. So in the single crystal one, you will have long range of repetitive arrangement or long range ordering of the atoms, we say. And in the polycrystalline material, of course, there will be more than one single crystal. That's why you'll be seeing this ring type of structure, not the spots ones. And also it has short range ordering. Okay. So this is the difference. Like polystyrene, you can say the bulk one, like bulk powder material, not amorphous, but bulk material, bulk crystalline material. And in single crystals, there are only diffractions will be clear. Like for single crystals, we take the crystals for single crystal XRD, and for the polycrystals, we take them for powder XRD. So those are a little bit different, because in single crystal, you want to know the crystal structure. So X-ray has to like penetrate, and X-ray has to come inside the crystal lattice and give you all the informations. But on the powder XRD, if you let's say this is a sample holder, okay, and this is the space. Let's say this is a glass slide, and there is some certain space where you can load your sample. This is a powder material, okay, and you are going for PXRD, like powder XRD. Then X-ray will just fall on the surface and diffract, okay, and that's how detector is there, and you will get some peaks, okay, whatever. And in single crystal, here in single, I'm just writing SC. So in single crystal, the X-ray will come and it will give you the inner structure. So X-ray has to really penetrate the single crystal one, but in polycrystal or powder, you don't need to do that. So yeah, X-rays are like, of course, X-rays are invisible, so that they mostly travel in straight line and can pass through the opaque object. So uh, in properties of X-ray, you must remember that if the electric field, let's say you already know about the plane polarized light, right? So the X-ray is has to be plane polarized. So there is some. I'm not going too much details. I'm just giving you the overview, because I believe you all know these things. Uh, so this is the one, and you already know the constructive and destructive interference and all. Then, of course, from this equation, we can say the one important thing is intensity. In the powder XRD pattern, if this is the powder XRD pattern, here we plot it as intensity, and here it is as 2 theta. This is in degree, like as in degree symbol. In the y-axis, as you can see, intensity is there. So intensity is basically the rate of flow of this X-ray energy through unit area perpendicular to the direction of motion, right? So average intensity, what is the main thing like to take away is average intensity is proportional to a square. That is the this term. Okay. Uh-huh. What? Hmm. So the intensity is basically measured by counting the number of photons incident on a detector. Okay, this detector basically counts the measures the number of photons which has fallen over your sample, and or by digit or you can also measure intensity by the like that by the blackening of the photographic film, though we don't use it here in case of normal powder XRD, but yeah, that's also possible. Okay, and okay, then there is some the like since it is a continuous spectrum or white radiation, you can say the X-ray. It so if the relative, let's say this is the relative intensity, then there is also a term called SWL or short wavelength limit. So this is, I'm sorry, just a sec. Yeah, so short wavelength limit is basically the maximum energy limit, or the since you all know energy and lambda, the wavelength, those are related. So the electrons which is stopped in one impact produce photons of maximum energy. Those are considered as short wavelength energy. So as you all know, E equals to h nu, and lambda is WL is the lambda minimum. This we can write it as HC by E. E is also EV, like this is one important equation and all. Now there is in this only if we draw the characteristic X-ray lines, means like if there is one atom and inside there is nucleus, right, and there is some electron. So high energy electron will be like, say, if this is the ray is coming and the low energy electron will be produced from here, and in the inner shell there is also outer shell, right? So in from the inner shell only the electron gets ejected, and those are only considered as the uh, characteristic X-ray. And also in case of any X-ray diffraction, like energy dispersive X-ray spectrum we collect, in that case also you will only be collecting the characteristic wavelength, like which will give you the which atoms are present. Like in your case, let's say NaCl, you are doing one of your crystal is NaCl. So Na has certain characteristics and Cl has certain characteristics. So and also both have like different uh, that in electron configuration system, like both have certain number of electrons in their valence or inner shell. So from the EDX spectrum, the same thing from the property of characteristics X-ray we are getting, like let's say sodium is we are getting a peak here at sodium, and also here this is chlorine. And not only we'll get this, we'll get like NaK alpha, ClK alpha. So K means for K shell. Like we know the shells of the, like in an atom, like K, L, M, N, those K among this. And alpha and beta, there are two types of those X-ray lines. So from this relative intensity, and this is lambda, right? So here we get such kind of characteristic X-ray spectrum. In any book you will find this. You just need to know like what are this and why are this important. Like these are characteristic of target materials, such as in this case target material is NaCl. So here you will be getting the X-ray peaks, for the intensity peaks for sodium and chlorine. Those varies, those are not like fixed, varies from compound to compound. Yeah, and the next thing I can tell about the X-ray production, the same thing. X-ray production is about, or if I can draw simply, let's say this is the K shell, the inner 1s, and this is the L shell. Yeah, this is the L shell 2s, let's say, and there are so many shells, right? So let's say this is the K alpha, and if there is one M shell, let's say this is 3s. So this will be a K beta. So alpha is, alpha lines are basically from n equals to 2 to n equals to 1, or n equals to 3 to n equals to 2, means just one atomic level gap, right? And beta lines are two atomic level gap, 3 to n equals to 1, or n equals to 4 to n equals to 2, like that. So selection rule will be an outer S or D electron cannot fill the hole left by the ejected 1s electron, but the p electrons can. Okay, so like synchrotron radiation source there is in France. Those are the, that one is the largest X-ray production. Okay, in the whole world. Now there are several uh, elements which we use for like to produce as an X-ray, like chromium, iron, copper, molybdenum. So you just need to remember the lambdas. Okay. So like in chromium, it's, I guess, yeah, I'm writing correct. 2.29, or iron is 1.93, copper is 1.54, and molybdenum is 0.71. These are all in Armstrongs. Okay, you just need to remember this. This is very important. And there is also certain beta filter kind of thing, where we filter the X-ray so that it doesn't directly fall on the detector. So those are the beta filters are there, and those are mostly like one Z, like one, like if this is the ZL, let's say 24 or 26, 29, and I guess this is 42, then the beta filters will be like the one less or one plus. So like Ti in chromium case, in iron case, in chromium, in copper case, nickel, and molybdenum case, niobium, so that it can absorb. the X-ray. So yeah, that's what it do. And in crystal and diffraction of X-rays, you need to know the law equation, the Bragg's law. What is the reciprocal? What is reciprocal lattice? What is the Ewald sphere? What is the importance of the Ewald sphere? Uh, and the intensities of diffracted X-ray. So to start with, diffraction of visible light by single slits, you have must have seen in your like physics experiments in class 2, like let's say this is a panel. Okay. Mm, so this is some dark ones, then there is some lighter ones, then there is some lighter ones, then there is some lighter ones, then there is some dark ones, then there are darker ones. So these are the kind of see the diffraction pattern of a narrow slit is like this. Now, if the slit is wider, then it will be visible as this. This much, like this. If let's say this is let's say this is one like 1 meter, or not meter, but it should be very less. But I'm just giving an example, and let's say this is 3 meters. So this means the diffraction pattern is narrower, will be narrow. Diffraction pattern will be narrower in this case for a wider slit by 3 times than the first one. Means how can you say that the let's say the larger the value of the lambda by a, the greater the spread of the spectrum. Okay. Now, from this, you can say that the reciprocal relation between the angular spread of the scattering or the diffraction pattern and the corresponding dimension of the object causing the scattering. Right. Now, yeah. Now, from the window, if you have a glass window in your home, you can see that most of the lights will get transmitted, right? Like in your pictures you have must have seen that if this is a glass, then there is this things going, these arrows are going, means a large number of parallel and closely spaced lines, those are getting transmitted, right? But in the crystals there are like the process is like 3D. Say this is the, or I can do simple one. Let's say this is a crystal and X-rays are coming like this, and it's not getting like not getting transmitted only like this, it's getting transmitted in all the directions. So the grating is important in source of light. So there are of course two types of interference, like the one is the constructive interference and another is the destructive interference. And yeah, and if we draw the cases, this is case one. So from here, you will get like this. So now the amplitude is 2 times and intensity is very high, right? So because these are all in phase, right? All in phase and high intensity. And case two is a slight displacement. Yeah. Mhm. It's not just crossing. So now from here, let's say it's coming to the center. So this is lambda by 4 phase difference, right? Now your intensity will be less. Now intensity will be less because this is partially out of phase. So you will be getting the lower intensity only. Now the third case is totally out of, or I can just do the right. As you can see, the total opposite. So yeah, from the picture you can see right. So this is lambda by 2 phase difference is there. Now this is totally out of phase, so no intensity will be getting. You'll be getting zero intensity. Now in the diffraction of light, where which will eventually give you the Bragg's law. So Bragg's law, let's say first we'll discuss about the law equation, which is very important, then the Bragg's law. So the in the wavelength of X-rays is, of course, as I previously told, is comparable to the interatomic separation in 3D crystals like the 2 to 3 Armstrong. So there are law equations for 1D crystal and also for the 3D crystals, like A sine phi in lambda, or A1 sine phi 1 in lambda, A2 sine phi 2 equals to n lambda, A3 sine phi 3 equals to n lambda. Law equation, all are law equations, but this is for 1D crystals and this is for 3D crystals. Now, Bragg's law is very important. So, what does Bragg's law state? Is, let's say this is coming like this is coming like this. This will be the theta, same theta. So, basically, uh, some of the X-rays are reflected off a plane with an angle of reflection equal to the incidence angle, right? The theta theta. But the rest are transmitted to be reflected by succeeding planes. Like, let's say if we name this XYZ, then XY equals to YZ equals to D sine theta. If we can do the trigonometry and all. So that's what the Bragg's law will give you the equation, that is n lambda equals to 2D sine theta. Now XYZ will be the n lambda. This is equals to XYZ. So this is the Bragg's law basically. Can you please mute yourself, Taposhi? Yeah, okay, fine. Now there are several orders of diffraction like direct beam, then the zero wide path difference is there. Now if the first order diffraction happens, then there will be one lambda path difference. Okay, I'll just write here. Direct beam means or everything is parallel in a vertical, sorry, horizontal manner. Zero path difference. Zero. I am just writing PD for path difference. Oh, let me write it. Now first order, like 100 on this is the diffraction orders, right? So this is one lambda path difference. Then second order, two lambda path difference. Then third order, that is 300 plane, three lambda path difference. Okay. So there are this is the order of differences. Now you should know the what are the reciprocal lattice. What are the reciprocal lattice? Basically, whatever we see from X-ray diffraction, like in the experimental, the result from we get from the experimental X-ray diffraction, that is the single crystal X-ray diffraction experiment. From we everything we are getting is in reciprocal space, not in the real space. Okay, so how reciprocal space is there? Let's say this is the crystal. This is the crystal lattice. Okay, and this is your x direction. This is your y direction. So this is your crystal lattice, and what how the crystal will you will see in the reciprocal lattice that we'll see now. So in a reciprocal lattice, we'll see like this. But your what we in the like how do you indicate the axis now? This is like a HKL, the Miller indices, right? So if this is 0, 1, 2, 3, or 4, whatever. Now here also you'll see this is 0, right? So 1, 2, 3, and here the same thing you must have seen in this manner. So it like rotates a slight, okay, in reciprocal lattice. So in reciprocal lattice, we also call like if something is there in the if this length is A, or let's say this length is A, we'll call this length as A star. Right, and from the theory, it has been proven that D star, D for the lattice space, that is 1 by D HKL, or A star is 1 by A, B star is 1 by B, like that, etc. So this is the difference between the direct space and the crystal structure. I'm always saying that you see the diffraction patterns in you from from a single crystal XRD, whatever you got, in the reciprocal space, not in the real space, and that's how we solve further to get the actual crystal structure. So there are in 3D crystal system there are 7 crystal systems you already know, and 230 space groups. So which the space groups which has the inversion center, those are known as centrosymmetric, and some space groups which have no symmetry element that can change the handedness. Means in the mirror we call na. Okay, let's say this is the or what can we do? Let's say this is the thing. If it change the handedness, then it's not. But so which space groups have no symmetry element that can change the handedness? Those are called the enantiomorphic. Okay. And there are chiral space groups as well. Now, we coming to the another point, Ewald space. So Bragg's law we are applying Bragg's law in reciprocal space. Right. Now the incident, let's say the incident X-ray photon has fallen, and it has and we write it as a vector form, right? In vector form, like k. This is just a indication, just a notation. With this must be a equal length to the reverse of the wavelength of the X-ray. So k vector is a vector in the reciprocal space with the length of 1 by lambda. Now, the wavelength of X-rays does not change with diffraction, okay? So, we can write, or we can rather draw, let's say this has fallen like this, and this has gone. Like this is K, and this is K bar. So, this is going here, and this is also coming like this. So, if we draw a parallel one, same thing, it's going like this. And here it is going like this. So this is the incident angle theta, and of course from the Bragg's law we know the diffraction angle is also same, the theta. And let's say this is one plane, this horizontal line, which is from Miller indices. We can write it as a HKL plane, and plane we write inside a bracket, and if it is direction we write in third bracket, like 110. Third bracket means direction. If we write 110 in first bracket, that means these are the planes. Okay. So yeah. So this is the thing. Now if we draw a perpendicular to this, let's name it as H. There's nothing like specific. I'm just naming it H. Yeah, and also name the specific corners as well. Let's say name is H, G, and O, and let's say this one then must be K prime, K bar or K prime, whatever. So now this angle is 2 theta. This is your basic trigonometry knowledge. Okay, now if we draw a circle taking this C point as the center, so how it will be? It will be somewhat like this. So here we have already defined that the length of k and k prime, those are equals to 1 by lambda. Now if from this we can derive OG OG, it's equals to k sine theta plus k bar sine theta. And since these are the vector terms, we can add mod to get the values. Right. So this will give you 2 sine theta by lambda. And according to Bragg's equation, and that is n lambda equals to 2d sine theta, 2 sine theta by lambda is equals to 1 by d. So you can say the h value is 1 by d. So 1 by d. So from this we can say k bar or k prime is equals to this. So this is the Bragg's equation in reciprocal space. And this is the Ewald sphere or Ewald circle, whatever you can call it. Now, we can tell that this is a diffracted beam with wave vector k prime will be present if and only if the vector k plus h lies on the Ewald sphere. Okay. So Ewald sphere is important to know. Now, coming to the scattering of X-rays by atoms, like atoms diffract or scatter X-rays because an incident X-ray beam, which can be described as a electromagnetic wave, it comes with an oscillating electric field and sets each electron in that atom into vibration. Now, this vibrating charge, such as an electron, emits radiation, which is in phase or coherent with the incident X-ray beam. The drawings I just drawn a little before, which are the case one, case two, like in phase, out of phase, or partially out of phase, whatever. Now, this electron therefore act as a secondary point source of X-rays. Now, there are elastic scattering, you all know. So the scattered beams, which are the most intense when parallel or anti-parallel to the incident beam, and weakest when it creates a 90-degree angle to the incident beam. Okay. So there are types of equations in this related to this field, like Thomson equation, or the Thomson equation is important. Now, scattering of X-rays, this is very important for a, let's say, uh, mostly we draw it as like this. F is the structure factor, and in x-axis we have sine theta by lambda, which has the unit of Armstrong, 1 by Armstrong. Right. Now let me give you some example. If this is the graph for calcium 2 plus, this is the graph for fluorine minus. Now you all know the electronic configurations of these two atoms, and you all can understand the how many electrons are there for each atom. Now, for a given angle 2 theta, the net intensity decreases with decreasing lambda because the phase difference gives a greater degree of cancellation for smaller lambda. Now, XRD patterns at higher angles are usually weak. Higher angles means around 2 theta of 60 to 70 degree. Now, in a X-ray crystal structure determination, it is difficult to locate light atoms like hydrogen and all, because their diffracted radiation is so weak. And here comes the factor, like the form factor. Okay, now form factor, which is the F. F. So F is denoted as form factor, or if the notation, it's equals to amplitude of wave scattered by an atom divided by amplitude of wave scattered by one electron. Now, if we describe it further, like there are two cases. Okay. So let's say there is a smaller atom, smaller size of atom, like hydrogen or carbon, etc. Those are smaller atomic number, right? So if the beam comes like this and different like this, comes like this and different like this. Now this makes the angle 2 theta, and this is the direct beam, right? So the phase difference you can see from here, from the center to this, to the surface. This is the phase difference, or PD I am writing. So this is the case for smaller atoms, and in smaller atoms you can see small path difference happening. Small path difference, or PD as I have written, with respect to the wavelength at edges of atom. Now, in case of larger atom, how does it behave? For large atom, there should be large path difference. And how the atom should be? It should be like this. So this is the large atom. Let's say bromine. It's a large atom. The one calcium I drew like that. So here one is going there. Here one is going here. Now you can see the two theta. And this is of course the direct beam. Now you can see the PD has been widened. So this is the large path difference with respect to the wavelength at each edges of atom. So from here we can describe this plot that the one has the large atoms, those has higher form factor, and in case of smaller atom, those are lower. So if we can arrange some atoms, like by giving you some examples, it will be clear to you. Let's say calcium 2 plus, if iron, let's say iron 2 plus, iron 3 plus, C H O O2 minus. Right. Now calcium has 20 means 18. Fe 2 plus means 26, 24. This is 23. Carbon is 6. H is 1. Oxygen is 8. This is 10. So the higher number of like electrons present, those who will be giving higher of form factors. Okay. So this was the basic one. In today's class I have covered. Now we'll be solving a few practice questions. Okay. I am going to show you the practice questions of this, of the first week one practice questions. Yeah. So the first one is, what are the wavelength? Like basically, I'm sharing the screen. You may not see now, but if you watch the video, then you will see that I'm sharing the screen. Uh, the first question is, what are the wavelength of copper K alpha and molybdenum K alpha? So here I have written copper is 1.54. You should always remember this, and molybdenum is 0.71. This is basically 1.5418 Armstrong, and this is 0.7107 Armstrong. Okay. And next question is, choose the correct statement. Copper K alpha is used only for single crystal X-ray diffraction, and there are four multiple questions, right? So copper K alpha, as you can see, the lambda value or the wavelength is 1.5418 Armstrong, whereas for molybdenum it is 0.71. So molybdenum has a smaller wavelength. Okay. Now, so smaller wavelength means energy is inversely proportional. So it has a stronger energy. So in case of single crystal XRD, like X-ray has to penetrate it and go through the single crystal so that you can get the inner information, inner crystal structure, right? So that's why a strong element would be needed, a strong energy, a strong element which possesses higher energy. So that's why for molybdenum we use for single crystal XRD, and copper we use mostly for powder XRD. And also copper, it provides good resolution materials. Okay. So initially, what now we have come to a conclusion that copper is good for PXRD or powder XRD, and molybdenum is good for single crystal XRD. Single crystal XRD. Now, there are questions like first option is copper calf is used only for single crystal XRD. That's not correct. Molybdenum is for no, is not used for powder X-ray. Both can be used for powder XRD or both can be used for single crystal XRD. Now here we have to think a little bit. See, uh, copper is mostly used for PXRD only, like especially for organic or inorganic compounds which has low to medium elements like low to medium atomic numbers, which gives us strong or good diffraction pattern. Now, molybdenum is mostly used as single crystal XRD, uh, and it is very useful for heavy elements also. But molybdenum K-alpha can also be used for powder XRD, particularly when the sample is highly absorbing or when a higher energy source is needed. Right. So we can, so here comes the answer that copper K-alpha and molybdenum K-alpha both can be used for powder XRD. Okay, now the third question is which of the following element is used as window in X-ray tube? The answer is very common. It's beryllium. Okay, so beryllium is used because first of all, you know that the X-ray tube window allows the generated X-rays to exit the tube while keeping the vacuum inside. So that is the function of of a X-ray tube window. Now beryllium is used because it has a low atomic number. Beryllium X-ray window. Beryllium, right? Now beryllium is used because it has a low atomic number. That equals to 4. So low absorption, it has low absorption for X-rays. It doesn't absorb much of the X-rays. Now beryllium is also mechanically stable and like in vacuum conditions also, because in a X-ray tube there must be vacuum condition, otherwise electrons will let's say collide with each other, and like we don't need that, right? We need X-rays to generate. We don't need to energy. We don't need the like lowering the energy. So and there are other options in the question as well, like magnesium, molybdenum, silver. So these are not suitable for to be used as a X-ray window. So the answer is beryllium. Now the fourth question is arrange the following in order of increasing intensity: metal jet source, seal tube X-ray source, rotating anode X-ray source, seal tube micro focused X-ray source. Now, see, seal tube. The first one is metal jet X-ray source. So, metal jet source is very high, like it is very efficient because direct metal vapor jet acting like acts as a target. And the next one is seal tube X-ray source. Now, standard X-ray source, it has a moderate intensity. Now, the third one is rotating anode. Rotating anode means it has the highest intensity among the all, like continuous rotation of the anode. It prevents overheating. Right, so and so it allows very high power. So it has the highest intensity it provides. Now the fourth one is a seal tube micro-focused X-ray source. Now it has high intensity than the standard seal tube X-ray source, which is at the number 2, due to the concentrated spot size, because it's the micro-focused source. So it has a moderate intensity. Now, if we like draw an order or create an order. So the first one will be the fourth one, seal tube microsource, seal tube micro focused X-ray source. Then the one is seal tube. Okay. Then the jet one, metal jet one. Then the highest one is the rotating anode. Yeah, I guess this will be the answer. Now the fourth one is There is no option. One is listed at 3, 1, 2. 3, 1, 2. Metal jet is the arrange increasing intensity. 1, 3, 4. Okay, 3 is the highest one. Okay, I have to then check once more about the intensity. For now, we can give it as 1, then 3, then 4, then 2. Yeah. And now, hmm, now the fifth one is the why are X-rays used to find the structure of the molecules? X-rays used to find, oh yeah, the simple one, the 2 to 3 Armstrong. Typically, we have in the crystals in 3D the interatomic spacing in between the 3D crystals, and X-rays have wavelength of 0.1 to 10 Armstrong. So that makes them good. Good electromagnetic spectrum to insert into the crystal structure, and we can do the diffraction studies where the interference pattern of the X-ray scattered X-rays reveal the atomic arrangement, right? So that's why we do the X-ray, like in medical applications we do also X-ray, right? So the first option is X-rays are very high in energy. No, not that much. uh, Wavelengths of X-rays are of same order of interatomic distance. Yes, X-rays penetrate, and because of the real life application, yeah, we do. But this is the most important one, the second one. So we'll just check answers. Which one is wrong? Both can be used to single crystal XID. Okay. So here we can see that copper K alpha, which is 1.54 Armstrong of wavelength, and molybdenum has 0.71 Armstrong of wavelength. So and generally we use copper for powder XRD and molybdenum for single crystal XRD. But when we don't need a heavy element or such thing is there, a lighter wavelength or a lighter energy element can also be used as a source, which is the copper, right? So yeah, fine. Then we go to the next week practice assignment. What symmetries are present in P1 space group? P for primitive and 1 for just a 360-degree rotation. One is the like principal form axis, the n-fold axis, n equals to 1. So P1, the simplest one. So this belongs to the triclinic space group, triclinic crystal system, and it has no symmetry elements other than the identity and the normal translation. And there is no mirror plane, inversion center, glide plane, rotation, screw axis, etc. Okay, so only inversion center is no there. If there would be, then that would be 1 bar. Only translational, yes. No inversion, translation, symmetry, and screw axis, no. So the second one. And S6 is equals to mirror plane. So S6, as you all know, S stands for the improper axis of rotation. And how many fold? Like n fold, n is 6. So S6 is a 6-fold improper rotation, right? Which is a combination of C6 and like reflection through a plane perpendicular to the 6-fold axis. So S6 basically is not equivalent to the mirror plane. Okay, let's say rather S2 is a mirror plane, like two-fold axis and a perpendicular mirror to that. So S1, we all know its inversion. S2 is the mirror plane. S6 is not equivalent to the mirror plane, but it also can generate mirror plane in certain conditions. So it's not the true one. The answer they have asked. So the third one is, which among the following space group does not have two mutually perpendicular mirror axes? So mirror axis here from the options you can see there are glide planes BCA, and glide means translation plus reflection. Reflection means there must be some involvement of mirror. So must be there should be a mirror in PBCA and FDTD. D is for the D glide, same thing. And here also PCA to 1 CA are the glide planes. So the left one out is the P21, 21, 21. 21 is the screw axis, means translation and plus rotation. Rotation plus half translation, like that. So there is no mutually perpendicular mirror planes. Those are the screw axis only, or the principal axis. Principal screw axes. Now the fourth one is the space group 4 by M means 4 means fourfold axis, and M is for mirror plane. Right. And generally we consider 4 by M is in tetragonal, yeah, tetragonal space group, and there we consider the primary axis is the C axis. So fourfold axis is must be parallel to C axis, and M is perpendicular to that C axis only. Or from the from the options also you can see that here the second one is both should be like the of course you will know that the infold axis, the principal rotation must go through one particular axis, and mirror is always perpendicular to that axis. It's a general conviction. So from the answers, from the options, you can see that the second option is, this one is B axis, this one is A axis, so we can't do that. This is automatically out. And for the tetragonal, we consider it as the C axis, the primary axis. So this one is would be the answer. Now the fifth one is whenever two mirror intersects at 90 degree, which symmetry element is generated? When two mirror perpendicular intersects each other, a twofold rotation axis is generated along the line of interaction, right? And this is a fundamental rule in like any crystallographic symmetry operations. So intersection does not generate a fourfold axis or a third mirror automatically. So the correct element generated will be a twofold axis. The first one. I hope so. So let's submit the answers. Yeah, score is 5 by 5. Okay, fine. Understanding of space groups. Uh, yeah, and equivalent points. So here also, yeah, these ones we have to draw and practice. So the drawing things we can do in the next class. I will start with some basic things like P2 and how the matrix operations, like we start with how the matrix operations functions. So we'll do that in next week. And as I have already told, the quiz week 1 assignment is supposed to be submitted on 6th, and the week 2 assignments as well supposed to be submitted on 6th, that is tomorrow. So I am not going to like do that. Okay, so yeah, that will be the today's class. It's almost 7:20. So yeah, let's end the class here only.